It's a subject most folks once viewed from a distance. A drug ring shattered in a faraway land. A gruesome murder in another state. Removed, detached, the kind of thing that always happens to us. Not anymore. Crime in this country has reached epidemic proportions. Over the past century alone, almost twice as many Americans have been murdered as have died in war. Crime is a disease from which no one is immune. And while every crime is different, all have one simple fact in common. In almost every case, the criminal leaves something behind. Pieces of an often complex and dangerous puzzle. It's the job of the Charlotte Crime Lab to fit these pieces together, to examine every shred of evidence until the facts are firmly established and the case is solved.
I guess you could say we're scientific detectives. Our job is to preserve, collect, and analyze physical evidence at the crime scenes. We then testify to the findings of these results in the court of law. And ultimately, we're there to assist local and area law enforcement agencies to connect the suspect back to the crime scene.
Crime labs have had a very brief history in this country, dating back to 1929 and the infamous St. Valentine's Day Massacre. Through ballistics testing, scientists were able to link bullets found at the crime scene to guns belonging to members of the Al Capone gang, proving beyond a doubt the value of science in the courtroom. The groundwork for the Charlotte Crime Lab was laid the very next year, when Chief Ed Pittman authorized the establishment of a small identification bureau. Over the years, the department and its responsibilities grew dramatically. Finally, on July 20th, 1969, two major events happened. Neil Armstrong walked on the moon, and the Charlotte Crime Lab officially opened for business in the new law enforcement center. Vincent Sievers was recruited from Dade County, Florida to serve as the first director, and by 1972, the various sections of the lab were fully staffed.
We now work with a full range of city, county, and state law enforcement agencies, and occasionally we are called in to assist in federal cases for our local office of the FBI and the Bureau of Alcohol, Tobacco, and Firearms. We have grown to be considered one of the top full-service laboratories in the country.
Let's get a shot of the hand next.
Okay.
The job of the crime lab almost always begins here, at the actual scene of the crime. Crime scene search unit technicians pore over every inch of the crime scene, photographing, measuring, diagramming, fingerprinting, collecting fibers, blood samples, paint chips, discharge cartridge cases, preserving any shred of evidence that may somehow provide a clue to the crime.
There it is.
The crime scene search unit is on call every minute of every hour of every day. Their caseload is staggering. In a recent month, the CSS unit responded to over 1,000 calls, took almost 4,000 photographs, lifted 900 fingerprints, collected 800 pieces of physical evidence. These items are first submitted to the Property Control Bureau for recording, then on to the appropriate lab sections for analysis.
This case began to fall together very quickly. We had apprehended a suspect within blocks of the crime scene. He evidently was wearing boots that were very difficult to run in. And evidently he had fallen down and severely sprained his ankle. And someone walking or limping down an alley in the middle of the night obviously is pretty suspicious, so the patrol officer stopped him. When they searched him, they found that he had what appeared to be over an ounce of cocaine on his possession, and there was blood splattered all over the front of his jacket. His explanation for this was that he just happened to come onto this crime scene. The cocaine was laying on the ground, he picked it up and ran off. The explanation for the blood on his jacket was that he'd cut himself several weeks earlier.
The suspect was immediately taken into custody and a gunshot residue test was performed. The clothing he was wearing was confiscated. He was booked on the cocaine charge, fingerprinted, and hair and blood samples were taken.
When a gun is fired, the tremendous heat and pressure generates a microscopic powder we call gunshot residue. This powder starts out as a gas, and it escapes through the cylinder gap or any other hole in the gun where gas can escape. The powder then deposits on anything within the vicinity of the gun, especially on the shooter's hands. The particles in this powder are extremely small. You cannot see them with your naked eye.
To obtain a gunshot residue sample, the suspect's hands are first swabbed with ordinary rubbing alcohol. The microanalyst can then determine the exact chemical elements contained within the sample. He does this by combining the power of a scanning electron microscope with the speed of a computer-controlled X-ray analyzer. In the microscope, thousands of electrons bombard the sample and create a TV image of the tiny particles, magnified up to 250,000 times. This gives the microanalyst a unique view of the sample's landscape. He can scan across its surface, then zoom in on one specific area for an even closer look. When the electrons hit the sample, they also give off X-rays. Each element emits these X-rays in a different way and contains its own unique wavelength. This gives the microanalyst a detailed roadmap to follow in determining the exact composition of the sample.
Gunshot residue consists primarily of three elements: lead, barium, and antimony. As you can see on the screen, PB is representing lead, BA is representing barium, and SB is representing antimony. Here on the peaks, these three peaks are lead, these two peaks are antimony, and these four peaks are barium. Finding all three elements on the same small particle means that without a doubt, this is gunshot residue. We also use this system to analyze other types of evidence, such as paint chips, building materials, or jewelry. However, in this case, finding gunshot residue on the suspect's hands is enough to link him with the firing of a gun.
While the microanalysis unit was performing the gunshot residue test, the chemistry section was busy with a few tests of their own.
Crack cocaine rather than cocaine hydrochloride.
They're concerned primarily with the analysis of drugs, blood alcohol, and arson debris. This evidence is important not only in identifying various substances, but also in determining the severity of the crime.
We can simply get a melting point determinations, and they're really fast. We were fairly certain when the material came in that it was cocaine. It was white and fluffy, it was in a plastic bag. But we were concerned about the weight because the possession of more than 28 grams of cocaine is a serious charge, that of trafficking. So in this case, the first thing I did was to simply weigh the contents of the bag. I found that it weighed over 29 grams, which is more than an ounce. That's more than enough to prove a trafficking charge if I could prove it was cocaine. The first thing I did was to perform a spot test.
A spot test is performed by simply placing a few drops of a special chemical mixture onto an unknown substance. This causes the substance to change colors based on its specific composition. Cocaine turns blue. Next, a sample of the substance was injected into the gas chromatograph mass spectrometer, GC mass spec for short. GC mass bombards the sample with electrons, breaking down molecules into fragments which can be easily identified.
The GC mass spec will give us an abundance of information about an unknown substance. And what it will do is it will take that information and compare it to a library that has thousands of known compounds in it. It will choose the 10 best matches and have them available to us to look at. In this case, we have a graph of the white substance that was found on the suspect, and also a graph of known cocaine. You can see here that there's a peak at 82 in the unknown and also in the known. At 182 here, and 303 here and here. Those are significant for the identification of cocaine. From looking at these two patterns, we can tell that the white substance found identically matches cocaine.
The spot test clearly indicated the presence of cocaine, as did the GC mass spec analysis. These tests, along with others conducted, allow me to say beyond any reasonable doubt that the material in that package does contain cocaine.
Back in the microanalysis clean room, both the victims' and suspects' clothing were thoroughly scraped down to collect tiny particles such as hair and fiber, potentially important evidence that may be almost invisible to the naked eye. With the help of a comparison microscope, these particles can then be compared to known samples taken from both the suspect and the victim.
This is an enlargement of what I saw under the microscope. On the left is a hair that we took from the head of the suspect. On the right is a hair that was found on the clothing of the victim. As you can see, the hairs are about the same width or diameter. And also, as you look at the edge of the hairs, you can see this clear area, which is what we call the cuticle. And you can see that it's present in both hairs. If you look at the coloring on the hair, they're both about the same color brown. You can also see throughout that coloring or the pigmentation area are some large, almost black clumpy areas, and it's clumping of the pigmentation, which is about the same on both hairs. I looked at these same type characteristics from the root end all the way to the tip end of the hair, and based on these characteristics, I've concluded that the hair found on the victim's clothing is consistent with the head hair from the suspect. I did the same type of comparison on fibers found on the pants of the victim and concluded that they were consistent with fibers from the suspect's jacket. The pieces of the puzzle are starting to fit.
The clothing was next sent to Jane Burton in the serology section. Jane began to analyze blood stains found on the clothing and compare these to samples taken from both the suspect and the victim.
First, I did an ABO blood typing on the samples. I found that both the victim and the suspect were type A. I had to go one step further, and that was enzyme typing by electrophoresis. Blood is very complex and contains various proteins and enzymes. Some of these enzymes exhibit different forms or types, which vary from person to person. Electrophoresis is a process we use to differentiate between these different types.
First, a blood sample is placed on a specially coated glass plate. Then, an electrical current is passed across the plate. This causes the blood's enzyme components to separate based on their electrical charges. The results form distinct banding patterns on the plate, patterns which help the serologist identify specific blood characteristics.
In this case, we're looking at a particular enzyme called phosphoglucomutase, or PGM. Here we have a standard blood sample from the victim and a standard blood sample from the suspect. You'll notice that the banding patterns between the two samples are different. This indicates that the victim and the suspect have different PGM types. Here we have a sample from the suspect's jacket. You'll notice that the banding pattern of this is identical to that of the victim's, but different than that of the suspect's. This proves that the suspect is lying. The blood on his jacket is not from an old cut. As a matter of fact, it isn't his blood at all. It actually matches that of the murder victim.
One of the most important pieces of physical evidence in this case was discovered quite by surprise. Patty Quinn, while examining the victim's clothing in the clean room, happened to discover a handwritten note tucked away in a pocket. And we suspected that this note was of great significance to this case. So in the meantime, the investigators obtained a search warrant, went back out to the suspect's apartment, and thoroughly searched it, and they came up with some very interesting evidence.
In a warranted search of the suspect's apartment, a letter and a diary were found on a desk in the apartment. The handwriting on these documents was used as known writing in this case. Several blank sheets of paper had also been confiscated from the apartment. I found that the watermark on the paper was the same as the watermark on the note found in the victim's clothing.
Perrotta next compared handwriting samples found in the suspect's apartment to the note found in the victim's clothing. He looked for similarities between the two, such as size, shape, spacing, and slant of the letters. He studied the writer's beginning and ending strokes, as well as the speed of the writing. What he found was amazing.
A handwriting identification is based on the fact that no two persons write exactly alike. Additionally, each writer develops unique individual identifying characteristics. A combination of these characteristics leads to a handwriting identification. This is direct evidence, much akin to fingerprint or eyewitness testimony. This is a photocopy enlargement of the questioned and known writing in this case. On the left side are the words found on the note in the victim's pocket. On the right side are words found in the letter taken from the suspect's apartment. I compared this questioned and known writing and found many similarities. For example, the distance between the numeral 1 and the word ounce is the same in both the questioned and the known writing. The angle formed by a line touching the tops of each of the letters in the word Friday in both the questioned and known writing is the same. The ending stroke in the word place on both the questioned and known writing is the same. After comparing the questioned and known writing, I determined that they were prepared by the same person, the suspect in this case.
Perrotta had established another link in the chain of evidence, a chain that was becoming stronger by the minute.
Perrotta's handwriting analysis added yet another twist to a case that was unfolding very quickly. Our chemistry section had established that the substance was in fact cocaine. Microanalysis had determined that the gunshot residue was present on the suspect. The serology unit had determined that the suspect was in direct physical contact with the victim. And we now knew that the note was a significant tie to the crime. But there was still a piece of evidence, that being the gun found at the scene, that we needed to investigate a link to the suspect. We would first submit the gun to the latent fingerprint section for evaluation.
Latent fingerprints are those which can't be seen with the naked eye. Some other method must be used to reveal them. In the field, these prints are obtained through the use of black powder processing. The powder is dusted onto a surface, and any prints revealed are then lifted with a piece of adhesive tape.
You know, this was a hard case from the beginning. There was no usable fingerprints found at the crime scene. All of them were smudges. We found a note in the victim's pocket that we processed for prints, but there was no usable prints found on the note.
The only item left to analyze was the pistol. The technicians use an unusual method to search for prints on guns and other objects with irregular, smooth surfaces. First, the object is placed in a tank along with a cup of water and a small container of cyanoacrylate, commonly known as superglue. As the tank is then heated up, the superglue and water combine to form a vapor which condenses on the object, revealing any prints that may be present on its surface. In this case, the superglue processing revealed a fingerprint clearly visible on the side of the gun. The print was dusted and lifted from the pistol, then compared to the prints taken from the suspect the night of the crime. On the left is a known print taken from the suspect. On the right is a print lifted from the gun. The similarities between fingerprints are known as specific points of identification. The examiners always establish at least 8 of these points before they conclude that 2 prints were made by the same individual. In this case, they were easily able to identify 10. Beyond a doubt, the print taken from the suspect the night of the crime and the print found on the gun were one and the same.
2 bullets were recovered from the victim's body, and another was found embedded in the car seat. Also, several cartridge cases were collected from the crime scene. It was our job to determine if these bullets and cartridge cases were fired from the same weapon, the pistol found at the crime scene. In firearm and tool mark identification, we're interested in the marks that one object makes on another object when the two come in contact. In this specific case, we're interested in the marks on a bullet that are left as it passes down the barrel of the firearm. A gun's barrel is rifled in a spiral pattern with a set of raised and lowered areas. These areas are called lands and grooves. Lands and grooves leave unique marks on a bullet as it passes through the barrel. In most cases, these marks are alike on every bullet fired from the gun. The same is true with the cartridge case. As the gun's fired, the firing pin, breech, and chamber walls each leave a unique set of marks on the cartridge case. And if it's an auto-loading weapon, marks can also be made as the case is extracted from the chamber and ejected from the gun. These marks are unique and reproducible. We therefore sometimes refer to them as the fingerprint of the firearm. Because of this, we can take bullets from the suspected firearm and compare those to bullets recovered from the crime scene. In this way, we can determine whether those bullets from the crime scene were fired from that firearm.
The firearms examiners use a simple yet highly effective method to collect test bullets from the suspected handgun. First, the handgun is fired several times into a specially designed water tank. The water acts as a cushion, slowing the bullets down gradually and protecting them from any damage that may interfere with identification. The bullets only travel a couple of feet through the water before falling to the bottom of the tank where they can be collected for analysis. Using a comparison microscope, the examiner then looks for similarities between these test bullets and those found at the scene of the crime.
The bullet on the left is the one I collected from firing the suspected weapon. The bullet on the right is the one that was removed from the victim. The lines you see here are the scratch marks left on the bullet as they pass through the barrel. When these lines correspond on the two bullets, as they clearly do here, we can say that both bullets were fired from the same firearm. Both of the bullets from the body and the bullet from the car seat were fired from the Smith & Wesson .45 submitted. Also, I compared the cartridge cases from the tests to the cartridge cases found at the scene. They also were fired from the Smith & Wesson pistol. There's no doubt about it, we have our murder weapon.
In addition to firearms identification, this section is called upon for tool mark identification and shoe print examination. In this case, we had a pair of boots reportedly taken from the suspect at the time of his arrest. And the crime scene search unit had taken several shoe print casts at the scene. If the boot matches the shoe print, then we can place this boot at the scene of the crime. Shoe print identification depends on several things: the way the individual walks and what that individual walks on, such as glass, asphalt, concrete, and so on. By walking on the concrete and the asphalt, in many situations there will be small little marks, cuts, and scrapes that will be left on the bottom of the sole of the shoe. Small cuts and imperfections on the bottom of a shoe will enable the examiner to determine if a particular shoe print was made by a particular shoe. For example, there are small scratches on this portion of the heel that match with that of the cast. In the upper portion of the heel, there are two pieces that are missing that also match with that of the cast. Again, in the center of the heel, you will note there's a small piece that is missing that matches with that of the cast. There are enough points of identification to determine that this shoe print was made by this shoe, thus placing this shoe at the crime scene.
McBraer's analysis of the shoe print provided the last piece of crucial evidence. The puzzle was now complete.
Largely on the basis of the forensic work in this case, the suspect was found guilty of first-degree murder and possession of cocaine with intent to distribute. He was sentenced to life plus 30 years. I wish I could say they were all this simple, but some cases take several years to solve. The art of criminal investigation has several elements: training, technology, creativity, common sense, and maybe just a little bit of good old-fashioned luck. Sometimes these things come together very quickly, sometimes they don't. There's one thing that I'm very confident of, and that is if there's evidence out there, we will eventually find it. And that evidence will be processed and analyzed thoroughly and presented in a court of law. We will follow the criminal's trail just as far as it leads us, and hopefully the criminal will find that that trail leads him straight to a dead end.